Our final example for maximum likelihood estimation, building on what we've seen on the previous videos, we'll do this for a gamma distribution. So gamma distribution depends on two parameters, alpha and beta, and it looks something like this depending on what those parameters are. So I've got this sort of rate parameter beta and then another parameter alpha, and depending on those I can have an internal mode or I can have a mode at 0. What we want to do is we want to say, well, if I believed my observations S1, S2, ... to Sn are drawn from a gamma distribution, but I don't know the parameters alpha and beta, what would my best estimates be of alpha and beta if I were using maximum likelihood estimation? Well, the first thing we would do is we would write down the likelihood of observing the sample S1, S2 up to Sn. So this is just the product of the probability densities evaluated at the point S1, at the point S2, at the point S3, and so on. Now, when I tidy this up, I'm going to pull through the product sign anything that doesn't depend on the observation itself. So I've got beta to the alpha multiplied n times, because it's in all n terms. So I've got beta to the n alpha, and then I've got this gamma alpha in the denominator multiplied in each of the n terms. So I've got it to the power n. The other terms, I've just got a product of the SI's to the alpha minus 1, and then when I'm taking a product of the exponentials, I've got e to the minus beta times the sum of the SI's. So the log likelihood of that is just taking the natural log of all of those. So where things are multiplied, they become sums. Where things are divided, they become subtractions. And so I will get to that as the log likelihood function. So all I need to do now is to differentiate that with respect to alpha and with respect to beta, set both of those derivatives to 0 and see what I will get. Now some of this, what I ended the previous slide with, is maybe easier said than done. Because if I differentiate this with respect to beta, that part isn't bad. Derivative with respect to beta, the first term doesn't depend on beta. The sum of the alpha minus 1 times log s, that term vanishes. The last term that only depends on gamma alpha vanishes. And then the middle term will quite nicely give me minus the sum of the s's plus n alpha over beta. Differentiating with respect to alpha is a lot worse. I mean, I can differentiate that. Yep. Setting that to 0 and solving is, of course, the hard part. So when I try to plug all of this through, the first part doesn't look so bad. I can write my estimate of beta in terms of alpha, or alpha in terms of beta, because I know that n alpha has to equal beta times the sum of the s's. That's fine. But even having that, plugging that into the second statement, the derivative of the log likelihood with respect to alpha, it's not really going to help me. The best I can say is that beta hat by maximum likelihood is n over the sum of the s's times alpha hat, and then the alpha hat has to satisfy this pretty awful statement. In reality, I would do that by some form of numerical method, because I'm not really going to find a nice tidy analytic form for that in general, for finding the estimates. So although the method is the same, I just wanted to end with an example where for the normal, I got some nice tidy closed form statements for the parameter estimates. For the gamma, sadly anything but. So yeah, we live in an imperfect world, but that is solvable.